a power transmission line carries current from 6000 volts generator to 3 loads ABC. The loads are located at 4, 7 and 10 kilometers from the generator and it draws 50 amps, 30 amps and 100 amps respectively. The resistance of the line is 0.1 ohms per kilometer. You can see that one in this particular figure. So what we need to find in the sense, so voltages at ABC we have to calculate. Find the maximum percentage of voltage drop from the generator to the load also we have to calculate. Okay. So this problem is very different compared to the normal KVL problems like that. Because here we cannot apply KVL or we cannot apply this voltage division. Directly we cannot apply. Okay, that is what I want to tell. So for example, if the situation is like this, this is A, this is B, this is C, and here 6000 volts is available. Then it is very simple to apply voltage division, because this 6000 volts is divided among these three resistors. For example, if you want VA, you can write 6000 into this node voltage is with respect to ground. So you're calculating across R2 plus R3 by total resistance R1 plus R2 plus R3. But if you do like this, it is a wrong method. We cannot apply this method in this particular case. Why? In the sense, here R1, R2, R3 are in series. There is no current division. Same current is passing through three resistors, so that we can apply voltage division to calculate VA, VB, VC, whatever it may be. But if you see the given problem, same current is not flowing here. 180 volts, you can observe here 180 volts, 180 amps is coming from the generator. Then after B, same amount of current is not going through the 0.3 ohms, because we have understood that 50 amps current is coming from node A towards downside. So it is nothing but you can able to treat this circuit like this also. See, so these are the three resistances, and here some current is coming, in the sense here some branch is there. They did not do that one. The 30 amps is going, in the sense here also some branch is there. Here also some branch is there. We don't know about these three branches, but we know that here current 50 amps is coming like this. Here current 30 amps is drawing like this. Here current 100 amps is drawing. So this is the analysis we have to apply. Okay. So anyhow, I'm going to start the problem now. See carefully. Just I have copied the problem once again. Now see carefully. They have given that for every kilometer certain amount of resistance is there. That is 0.1 ohms per kilometer. 0.1 ohms per kilometer. And we have to take these three resistors at different distances. One is at 4 kilometers, second one is at 7 kilometers, and next one is at 10 kilometers. So I'm taking those distances at first. So 4 kilometers from the generator, 7 kilometers from the generator, and 10 kilometers from the generator. So if you take 4 kilometers, how much amount of resistance will be created? For 1 kilometer, they have given 0.1 ohms. That means for 4 kilometers, 0.1 into 4, that means 0.4 ohms. For 7 kilometers, similarly, if you calculate, you will get 0.7 ohms. For 10 kilometers, you will get 1 ohm. But this 1 ohm is from the generator. This 0.7 ohms is also from the generator. This 0.4 ohms is also from the generator. So, instead of writing everything from the generator, For first 4 kilometers, you can take the resistance is 0.4. So we can represent using this resistor symbol 0.4. Okay. Next, from this 4 kilometers, you can take now 3 kilometers because from the generator it will become 7 kilometers. So here from the source up to this point it is 0.7, but already here 0.4 is over. So I am taking the next resistance is 0.3. In a similar manner, to cover total 10 kilometers, here once again I have to take 3 kilometers and here also I will get 0.3 ohms only. And they have given that it is node A, it is node B, and it is node C. And already I have given the explanation that same current is not passing through these three elements. That means these are not in series. So some current has been drawn from node A, some current has been drawn from node B, some current has been drawn from node C. So how much amount of current has been drawn from node A? They have given 50, 30 and 100 respectively. So 50 amps is drawn from A and 30 amps is drawn from B and 100 amps is drawn from C. 50, 30, 100. Okay. And they have given from the 6000 volts generator, the generated current is 180 amps. Okay. Now you can see the circuit in a simple manner. Okay. You can apply here KCL at node A. You can apply KCL at node B. Okay, similarly, we can able to apply for the normal circuits, how we are applying. Similarly, we can able to apply. You don't know what are the elements are connected to draw 50 amps. You don't know what are the elements are connected at B to draw 30 amps. You don't know what are the elements are connected at C to draw 100 amps. But you know that 50 amps have been drawn and 30 amps have been drawn and 100 amps have been drawn. So, if you apply KCL at node A, then 180 is entering, 50 is leaving, and some current X is leaving from node A towards node B. So, how much current is going from A to B is nothing but that is 180 minus 50, that is equal to 130 amps. Okay, it is 130 amps amount of current is going from A to B. That is what I'm representing here. It is 130 amps. And out of 130 amps, again, some current is drawn at B towards the downside. That is 30 amps they have given. So remaining current is going from B to C. If you apply KCL at node B, I'm writing here KCL at B. So entering current at B is 130 and one of the leaving current they have given, that is 30 amps. And we know what is the current which is going from B to C. B to C we don't know. So that is what I'm taking again here. Y is the current moving from B to C. Okay, so easily we can able to write Y is equal to 130 minus 30, that is equal to 100 amps. That is equal to 100 amps. So 100 amps is going from B to C, and that 100 amps only coming down. This is what we can able to observe. But actually what we need to calculate, if you see the question, we need to calculate find the voltage at at loads ABC. Okay, at loads ABC we have to calculate the voltages. Okay, we have to calculate the voltage. Now we got all the currents. When you know all the currents, how to calculate the voltage? First you try to calculate what is the voltage across the 0.4, what is the voltage across the 0.3, what is the voltage across the another 0.3. So easily we can able to calculate current passing through the 0.4 ohms is 180 and resistance value is 0.4. So what is the voltage drop? Product of these two. Because it is 0.4, 18 into 4 we have to take 40 plus 32. It is 72 volts. Okay, 72 volts will be there across the 0.4 ohms. Out of 6000 volts, 72 volts is available across the 0.4. Now, remaining voltage will be there at node A. You no need to see the entire circuit now. So, for your convenience, I will take this circuit. I will copy this one and I will paste here. Okay, so you see here carefully. This is the source. This is the source. 6000 volts is the source. Out of 6000 volts, 72 is gone. Okay, across 0.4 ohms, 72 is available. Remaining voltage should be available at node A because this entire circuit can be equivalently written like 6000 volts is the battery and it is connected to 0.4 ohms and across this one you are observing 72 volts is gone and here node A is there. That's it. Like this you can see this entire circuit here, whatever it may be there, that entire circuit we can able to take like this. Simply 6000 volts is a DC source connected to 0.4 and 0.4 is having the voltage is 72 volts. Remaining voltage must be available at node A. So at node A, if you apply the KVL in this particular loop, simply we can able to take at node A certain amount of voltage is there. So that voltage I can take like this. So this is called VA. So VA is equal to simply I can calculate 6000 minus 72. How much will get? 5009 28 volts will get. So this is VA. Okay. So VA is nothing but 5928 we got. Okay. Again, I'm already copied now. So again, I'm taking. So I have taken like this. Okay. So just I will erase the unnecessary things for better understanding. Okay. Now you see, what did we get? We got here VA is equal to 5928 volts. 5928 volts we got at node A. Okay. Then what is the voltage across now? 0.3 ohms. Voltage across 0.3 ohms. That means I'm calculating the voltage from A to B. We don't know the current passing through 0.3 ohms. That is 130 amps. So 130 into 0.3 if you perform, you will get the voltage across this 0.3 ohms. So voltage at 0.3 ohms or voltage from A to B is equal to 130 is the current and 0.3 is the resistance. Ohm's law. Simply you will get the current, the voltage across this one, that is 39 volts. So here the criteria is, here node A is there. Node A is at 5928 volts. 5928 volts. This is node A. This is like a source node. It is a source for the rest of the circuit. And here one resistor has been connected. That value is 0.3 ohms. And across this one 39 volts is there. And here node B is there. Now you see it is a simple circuit consisting of the source is 5928. So I can redraw this one like this. Source is 5928 volts and here I can take 0.3 ohms and which is having the voltage is 39 volts. Here node B is there. I don't know what is the voltage across this node B. So this is what I need to calculate, VB. So simple KVL you apply. KVL is VB is equal to supply voltage is 5928 minus 39. Simple. So it is equal to. So this is the voltage at node B. Similarly, we have to calculate the voltage at node C. Okay. So after getting the voltage at node B, we need to calculate the voltage across this particular 0.3 ohms. Once again, one more 0.3 ohms is there. Na? How much will get that one? It is simply 30 volts will get. So just simply we have to subtract 30 volts from this one. So VC is equal to, you will get 5889 minus 30, that is equal to 5859 volts. In this manner, we can calculate the node voltage C.